Floating point can also have some limitations. The first limitations are very common among all kinds of number representations: overflow and underflow. So for overflow, it happens when the result of an operation is too large to be represented, or the exponent is too large to be represented. For underflow, it happens when the negative exponent is larger than can be represented, or the result is even smaller than the smallest denormalized floating point. Depending on the system, if a trapping is enabled, overflow or underflow will trigger an exception. Otherwise, for overflow, the operation will result in appropriate infinity, so positive infinity or negative infinity. For underflow, the operation will return positive or negative 0. Another thing is that what if the result rounds off the end of significant? Like irrational numbers pi, 1/3, you can never have enough bits to represent these numbers, right? So they need to be rounded. Floating point have different rounding modes, but the most common one is round to the nearest representable floating point. Just to illustrate, we talked about gaps between denormalized numbers and gaps between normalized numbers. If the result that we need to represent lies inside these gaps, we will need to find the nearest floating point and use that as the representation. Before, we already calculated the gap between each denormalized number and learned that they are evenly spaced. But what will happen when we increase exponent? Will the gap between each representable floating point number stay the same? The answer is no. And the width of the gaps depends on the exponent field. For example, on the left, we have exponent equal 2. On the right, we have exponent equal 3. If we choose a same bit in the significant field, here we're choosing the leading bit, and flip it, we can calculate the gap between these two numbers. We can see that when the exponent is 2, the gaps equal 2. When the exponent is 3, the gaps equal 4. So the gap between each representable floating point is actually increasing as the exponent increases. Here is another picture. You can see that the distribution of values is denser towards 0, and the gaps just get wider and wider. So the limitation is that we only have 32 bits, so we can only represent 2 to 32 distinct values. Just because we can have a bigger range, it doesn't mean that we get more numbers. We gradually lose precision as we have higher exponents. That's why the gaps become wider and wider. So one of the resolutions for this problem is to utilize more bits. That's why we have double precision, which have 64 bits and give us a lot more precision. Another limitation is that floating point addition is not associated. So when you add a small floating point plus big floating point plus small is not equivalent to small plus big. This is due to rounding errors that we mentioned before. Floating point will approximate small plus big differently than small plus small. That's why when you do equality tests with operations involving floating point, it's very likely that you will get the wrong result. Even simple arithmetic operation like 0.1 plus 0.1 plus 0.1 is not going to equal 0.3 because of these rounding errors. Another thing is that despite being seemingly more accurate, floating point cannot represent all integers even. Remember the gaps between each representable floating points? It becomes wider and wider. At some point, the gaps becomes wider than 1. Starting from there, we cannot represent all the integers anymore. For example, for 2 to the power of 24 plus 1, the actual value is 16,777,217, but in floating point, it will return 16,777,216 because the actual value is actually not representable in floating point format. This is a small exercise. Let FP12 equal number of floats between 1 and 2, FP23 equal number of floats between 2 and 3. Which of the following statement is true? Basically, we're trying to compare the number of floating points between 1 and 2 and 2 and 3. The correct answer is A. So there will be more floating points between 1 and 2 than 2 and 3. So let's write down 1 in scientific notation first. It's equal to 1.0 times 2 to the 0. And 2 is equal 1.0 times 2 to the first. Right? So between 1 and 2, all the floating points are in the format of 1, then point any number insignificant, then times 2 to the zeros. Since there's 23 bits for significant, we can make use of them all. There are approximately 2 to the 23 floating points in between 1 and 2. And then let's write down the floating point representation for 3, which is 1.1 times 2 to the first. Okay? Because exponent is 1, we move the binary point 1 digit to the left. It gives us 1, 1 as binary. That will equal 3. So between 2 and 3, the floating points are in the format of 1.0, then any number insignificant, then times 2 to the first, right? So we have 1 bit fixed, and the rest 22 bits are all can be used. So there are approximately 2 to the 22 floating point numbers between 2 and 3. That's why there are more floating point numbers between 1 and 2 than 2 and 3. So we have big floating point number which equal to the 60, and the tiny floating point number equal to the negative 15, and big neg equal the negative big. So what will the following conditionals evaluate to? The first one is big times tiny and times big neg equal big times big neg times tiny. Second one is big plus tiny plus big neg equal big plus big neg plus tiny. I encourage you to pause the video and think about this question. The answer is C. So the first expression will evaluate to true, because when we're multiplying two floating point number, we add their exponents first and then multiply significand. Here, the significand is essentially 1.0. For the exponents, there is no overflow, so two results will be equivalent. So for the second expression, on the right, we have big plus big neg, which give us 0, plus tiny, which will evaluate to tiny. But on the left, you will actually evaluate to 0. The reason is that big is a very big number and tiny is a very tiny number. So when we're trying to add a tiny number to a big number, we don't change the exponent, only the significand. So when we add 2 to the 60 and 2 to the negative 15, we need to change the significand, which is 75 digits after the binary point. But the size of the significand is only 23 digits, so we end up adding nothing to the value. 2 to the 60 plus 2 to the negative 15 is still going to be 2 to the 60 in practice. That's why the expression on the left will evaluate to 0, and the whole expression will evaluate to false.